Hi, I am Vaibhav Bedi from Ester Bhopal, and today we are going to discuss some of the concepts of resonance. Though in previous video we had already discussed a lot of concepts, but still few are left. So I'm going to cover them up in this video. Okay, now our first topic is equivalent resonance. Now what it means is that we have a resonance in which the contributing structures have same potential energy. So what it means is that in a chemical reaction, all of these structures will contribute equally. Okay. Now, for example, we have an acetate ion, and if we draw its contributing structure, it looks almost same. It is actually the same thing. So if we make a resonance hybrid, we can easily state that every oxygen will have same amount of charge, and every bond, though it is carbon double bond or carbon single bond O, that will be same in both the contributing structures. Okay, now we can do the same in this type of molecule as well. I have left it as an example. Now our another topic is dancing resonance, which is very important because this is the most stable resonance ever found. So if you find any molecule doing dancing resonance, you can state that it is the most stable molecule of the pool. Okay, now why it is most stable is, now let us consider a propane. We know that propane has sp3 hybridized carbons, but because it is a ring, I am considering propane, which is cyclic, cyclopropane. Now in a ring of 3 carbon, the angle should be of 60 degrees. The angle should be of 60 degrees, but what our hybridization concept says, what our hybridization concept says that the this angle should be 109.5 degree, but the present angle is 60 degree only. So there is a lot of angular strain. Due to this angular strain, the molecule is somewhat crushed, and the bonds bend outwards or perpendicular to the molecule. Now if I attach a CH2 positive on any carbocation or anything which accept electron, what it will do is that due to this pure orbital, it will attract this bonded electrons towards itself, and it will start resonating. So every bond will start resonating with this pure p or any carbocation or any element which accepts electron. So this makes it a more stable structure or more stable system. Okay, now we are heading on to electromeric or mesomeric effect. Now actually there is not anything special in this. Now if we consider resonance in straight chain compounds, we can refer it as mesomeric or electromeric effect. Okay, now next is positive R or positive M effect. Now this effect is shown by those groups which tends to donate their electron densities to any carbon chain or any element. Okay, now for example, we have this carbocation placed there, and right next to it there is oxygen which has lone pair. Now what it will do, it will donate its lone pair into its pure p orbital, and this will get stable. In this, the octet of carbon was not complete. In this, each and every octet is complete, therefore it is stable, though oxygen has positive charge, which makes it bit unstable. Okay, now what is minus R or minus M effect? Now these are shown by those group which tend to accept or which tend to extract electron density from any carbon chain or any element. Now this may be aldehyde group or acetyl group or nitro group. Now for example, we have nitro group at benzene. So what it will do is, this nitro is highly electronegative, and we have slight positive charge over nitrogen as well. So it will extract these pi bonded electrons next to it, and this will become a structure like this. Now these two bonds are still there, I have mistaken there. I have not drawn it, so pardon. Now there is an exception as well. There are many groups, in fact not too many, but there are many groups which can show both the effects, that is plus R effect and minus R effect simultaneously. It depends only how they are attached. Like we have Ester and 2-degree amide, which can show this both effects. Now taking Ester, if I connect any group towards its C double bond O end, then it will become minus R, because we have, in previous video we discussed that there is a polar pi bond, and which wants to extract electron from its group, from its nearby group. Okay, now if I connect oxygen end towards any group, then oxygen has lone pairs, two lone pairs, therefore it will act as electron donating group, so this becomes plus R group. Now the same thing happens with 2-degree amide as well. We can easily see there is an electron withdrawing group and there is electron donating group, and the effect just only depends at which side we connect to the group. Okay, coming to the next slide. Now we can predict the stability of the contributing structures if we follow the sequence. Now the trick is you have to follow the sequence strictly. Means if I have written at first place that the group must have, or the contributing structure must have complete octet, then we have to search complete octet rule only. Means if we have given 5 or 6 or any pool of contributing structures, first we will go for complete octet, then only we will search for maximum number of resonating or pi bonds. Okay, let me first explain what these rules are. Now first rule is, first and foremost you have to give priority to octet completion. For example, in this each and every carbon has complete octet, but in this one carbon has incomplete octet, so automatically this first contributing structure will be more stable. Now our second rule is that the contributing structure must have more number of resonating or pi bonds. Okay, now if we consider this example that I have taken, now in first and third the resonating structures are same. Means this will show 3 resonating structure, this will also show 3 resonating structures, but the second one will be able to show only 2 resonating structures, therefore it's least stable, so it comes to an end. And in our previous video we have discussed that unidirectional resonance is more stable than bidirectional resonance, and clearly in first case we have unidirectional resonance, whereas in third case we have bidirectional resonance or polydirectional resonance, therefore this stability order comes as this. Now our third rule is that the contributing structure should have minimum charge density. Means that the first of all the charge density is same along a period. This we have to keep in mind, and in example we can easily see that there is one molecule which is not charged and there is second molecule which is charged. So if we have a contributing structure which has no charge at all, means there is no polarization or no charge, that is more stable. That is what I have written here. So the stability will be, first will be more stable than second. Okay, now coming to our fourth rule, which is electronegativity. Means if a negative charge is placed on a more electronegative atom, it will be more stable, and if we have a positive charge on more electropositive atom, then it will be more stable. Okay, now for example we have negative charge on carbon, and in second structure we have negative charge on sulfur. Though they have almost same electronegativities, but sulfur is still more electronegative. Therefore, a negative charge on sulfur will be more stable. Therefore, the second structure will be more stable. Okay. Now coming to our fifth rule, which is charge separation. Now in this, what actually is charge separation is that if we have a like charges, if in a contributing structure there are like charges, they should be placed more away. That is simply because there will be repulsion if they are more close to each other. Like, and if we have unlike charges, they should be as close as possible. It means they will attract and they will form a bond, and as they form a bond, energy will be released. So like for example, in this no charges are created. So according to rule number 3, we should have minimum charge density. So first is the most stable, but now trick comes that out of B and C, which is more stable. Now we have read that unlike charges should be more close to each other to get attracted and form a bond and release energy. Okay, so our second B is more stable and then the third. Okay, now let's do an exercise which will help in our application part more. Okay, now we have this type of molecule in which there are 3 pi bonds simultaneously occurring to each other. Now if we draw their structure, that how they will be bonded to each other, we can easily see that the first and the third pi bond are parallel to each other, and for resonance it was mandatory that the structure should be planar. Therefore this first and the third pi bond will do resonance with each other, whereas this pi bond, which is in z axis, will not resonate with any of the pi bonds next to each other. Therefore there is resonance in only first and third. Okay.